So in this one, I don't think you would need to use conservation because it's only asking you to solve for component forces. Like it's only asking you to solve for like, the change in potential energy, or, like the work due to a certain force. So like when you're doing that, you're basically just finding pieces. Like when it says potential energy, like I'm like, okay, well I start here and then I go this high. So it's like if I have the mass times gravity times the change in height, what is my potential energy? So these are basically like just pieces. So it would be essentially like your initial potential energy, right? Like you'd have mg, like 2 meters minus mg times 1/2. And so your net potential energy is just like 3/2, right? Times mg. So it's just asking for like a piece for the change. You can plug in all of the components into the equation and solve for these things, but the problem doesn't explicitly ask for it. It also asks for like the work done by a certain force. So when it says work done by a certain force, it's like taking this Henry is pushing and he's pushing this block up this wall, and we want to know the work that he does. So when we're looking at work due to a certain force, we are just using like the equation, right? Work is equal to FD cosine of theta, right? Or the dot product basically between, some force, and then what it is essentially like acting against. So we need the force that's acting in the direction of motion. So the way that we break up the vector here is that we have F and then we have an X component and a Y component, and we notice that the Y component is going to be along the direction of motion. So we need the component of the vector that's going to be parallel to the direction of motion that's going to be acting along that direction. So we're going to take Fy, and we're going to say that W is equal to Fy times D. So yeah. So we just need the component acting in the right direction. So yeah, basically if you wanted to set this up with conservation of energy, you could. And it says that like he's trying to get the block over the wall. So the way that I modeled it, I just said that the maximum height was 2. So I assume that if he gets to like 2 meters high, it's going to tip. But I just modeled this as the max. If the problem asks for something more, I think it might need to be a little bit more specific. But so if we look at the initial state, it's like against the wall, and then he starts pushing. So we're going to say initially, we're going to say it's at 0 and it's at a certain height. And then our intermediate non-conservative work, we have non-conservative work from the force that's like being applied to push it up. And then we also have non-conservative work from like the friction, right, that's acting down. So we have this Fk, and then this is like the Fy piece, like pushing it up, right? Okay, so those two pieces are contributing to the work. So my non-conservative work term here has like 2 things, right? I have this outside force, and then I have this outside force, right? So I would have to put them both into here. Okay, so like I have an initial potential energy, and then I have in the middle I have 2 outside forces, right? So initial potential energy, 2 outside forces that are kind of acting against each other here. And then I have a final gravitational potential energy at the top. So state 2 is like at the top here, right? State 1 and state 2. So this is, okay, state 1, and this is state 2. Okay. Yeah, and then if I'm trying to look at those, I would just take the distance. I'm going to call this delta y, so like the change in height that the mass travels. And then I'm going to say, okay, here's the force times the change in height minus, right, this force times the change in height for the 2 outside forces. Okay, so yeah, in this problem, it just asks you to solve for the components. So like this isn't really necessarily useful, but if you just want a little bit for understanding, if you were asked to maybe find more things in this problem, hopefully this helps. But yeah, and then one other thing too for the normal force. So if I take the mass and I kind of bring it off to the side, so this is, my mass over here, right? And I just moved it over here. Okay, so same block. And I drew my free body diagram in here, so I would have the weight of the object. I would have the normal force that's perpendicular to the surface that the object is touching, right? It's always perpendicular to the surface. And then I had this force at an angle, this force F, and I'm breaking it up into two pieces. So if I do sum of forces in the x direction, right, because I want to find the normal force, I have no, acceleration into the wall. It's going to be flat up against that wall. So I'm setting it equal to 0, and I can say that the normal force is equal to this f of x component. And so if I look at this angle, f of x is directly across from the angle that they give me, so that's f sine theta, the magnitude of f sine theta. And I can plug that in to find my frictional force, and I can say my frictional force is equal to mu f sine of theta. So I know it's a little weird for the normal force because we're used to it being like a weight or something, but you can kind of think of the normal force as just like the pressure between a surface. And that's really what's causing the friction, right? If I have a block and I'm pressing it really hard into the surface and trying to slide it along the same surface, that force that I'm pressing it into that surface is what's going to contribute to like the overall friction.